Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I am one of the co-founders and teachers here, along with my younger brother AJ Raj. As you can see, we have a new Algebra 2 lesson, and in this lesson, we're going to skip forward a unit because this lesson was also highly requested by some students who are studying for their final exams, just like rational functions and their graphs were. So again, if you have any requests, please you can email us or you can comment down below and we will do our best to answer those requests with video lessons. So in this video, we're going to be talking about inverse relations and functions. This is going to be part 1 of what I believe is going to be 3 to 4 videos on this topic, just so I can go as in-depth as possible, go over different problems and scenarios, and then I'll have like a last video that sums up some practice problems you can anticipate to see on an actual assessment. So in this video, we're specifically going to be understanding what an inverse is. So I'll be defining what an inverse is, and then we're going to find how to find the inverse of a given relation or function, and we're going to find this inverse of whatever relation or function we're given using different methods such as a table. We're also just going to be deriving the inverse from looking at an equation of a relation or a function, and we'll be graphing. So those are the 3 things we're going to go over today. Before I get into the video, I just want you to take a look at this image I have up here. So this is an example of a function f and its inverse f, and then we denote it by saying f to the power of -1. That's how you'll write an inverse, and I'll go over that again. So later on in the video. So in f, we have 2 different ovals here, and in this first oval, we have A, B, and C, so we can call this our first set. You can think of each oval as a set. And then our second oval here has 1, 2, and 3. So this is our second set. Whenever we have a function, we usually put our inputs, our domain, or our x-coordinates in the first set, and then we put our output, our y-coordinates, or our range in the second set. So A, B, and C belong in the domain. There are x-coordinates. And if you see, there are arrows pointing to corresponding y-coordinates. So for example, A points to 3. So this would be the point A, 3, because 3 is a corresponding y-coordinate. These belong in the range, like I just said. To find the inverse of a function, so to find the inverse of f, we're pretty much just simply going to switch the domain and the range. So here we had our 1, 2, and 3, our numerical values as the range, but to find the inverse of f, we're going to make them our domain. So if you can see, we swapped the 2 ovals, so the second set of the function f becomes the first set of the function f inverse. And then the first set in the function f becomes the second set in inverse of f. In the inverse of f. So in this case, we just switched A, B, and C, and 1, 2, and 3. We made our range our domain, and then our domain our range. So we'll get more into that, but I just wanted to show you an image of what we're going to be talking about today. So first, let's talk about the purpose of this lesson. Why are we learning this? So here's the objective. So this is the thing that I want you to keep in your head and what I want you to take away after this lesson is over. We want to find the inverse of a relation or a function. So before I even get into whatever else the slide covers, let's talk about what a relation is and what a function is. So a relation is this relationship between 2 sets of numbers. So it connects these 2 sets. And it's a collection of ordered pairs that contain one object from each set. So as you saw on the previous slide, we had 2 sets. So a relation is pretty much going to be a collection of ordered pairs that consists of an object from each set. So one object from the first set and one object from the second set. So if you have object X, let's call it object X, that belongs in the first set, and you have another object Y, that belongs in the second set, you know that there is a relation if the ordered pair x, y belongs in that relation. So you know there's a relation between x, and you know there's a relation between y if the ordered pair x, y belongs in the relation between the 2 sets. I know it's a bit confusing to understand, but hopefully when we get more into the definition and then some problems, you'll be able to grasp it better. And a function is an example of a relation. So a function is a binary relation. So when we say binary, we mean 2. So a function is a relation between one input, so one element of the first set, and one element of the second set. So hopefully you remember when we talked about functions, what makes a function? Well, remember when we did the vertical line test, and I know they covered that in our Algebra 1 course as well. I also covered it at the beginning of this Algebra 2 course. The vertical line test is pretty much when you have a graph of what you don't know. You have a graph of a relation, and you're trying to determine, is this a function or not? And you draw vertical lines up and down, and if the vertical line touches two parts of the function, then it is of the relation of the graph, then it's not a function. So what does that mean? That means that multiple elements from the domain, so multiple x coordinates, can correspond to the same y coordinate. But this is the key takeaway. Multiple y coordinates cannot correspond to the same x coordinate. In other words, you can have multiple inputs correspond to the same possible output, but you can't have multiple outputs correspond to the same possible input. That's how functions work. So if that rule is violated when we look at these sets, then we know we're not looking at a function, we're looking at a relation. So here are some other properties of inverses, relations, and functions. If a relation pairs elements A of its domain to element B of its range, the inverse relation pairs B with A. So like we said, when we looked at function f, we had its domain, we had A, B, and C in the domain, and then we had 1, 2, and 3 in the range. In this case, you saw arrows pointing from A, B, and C to either 1, 2, or 3. In that example, the arrow was going from A to 3. So A was pretty much like our element A in this example, and then the 3 was like our element B in this example because A belonged to the domain and B belonged to the range, and there was an arrow that was connecting them, so they're paired in the relation in function f. However, when we look at the inverse, like I said, we're swapping the domain and the range. Therefore, the inverse relation is going to, instead of pairing A with 3, we're going to be pairing 3 with A because we swap the domain and the range. So just like here it says, a function will pair element A with element B, the inverse is pretty much going to swap them and pair B with A. So if the ordered pair AB is an ordered pair of a relation, then the ordered pair BA is an ordered pair of the inverse. So like we said before, if A is related to, like we said before in the last example, A was related to 3, that A was an element of the domain related to 3, which is an element of the range, and we could write the ordered pair A3 because that was a relation of the function f. Because that was an ordered pair and it was a relation of the function f, then we can automatically assume that BA, which if we rewrote that same example would be 3, comma A, that would be an ordered pair of F inverse. So that's just how you just pretty much, if you have an ordered pair XY, to find that same ordered pair that belongs under the inverse, you're pretty much going to swap the X and Y coordinates. So if I had the ordered pair 1, 2 that belonged to function f, if I wanted to find what that ordered pair would be, what the relation between those coordinates would be for f inverse, I would swap them and then I would get 2, 1. Pretty straightforward. So if both the relation and its inverse happen to be functions, they're inverse functions. Again, we test to see if a relation and its inverse are functions by 1, you could graph them and do the vertical line test and make sure your vertical lines do not hit 2 or more parts of the relation and its inverse. Do not hit do not hit the function and its inverse. Sorry, the relation and its inverse more than once. Or you could look at these sets. So you could look at your first set and your second set, and you could see, do multiple components in my range correspond to the same component in my domain? That would be an indication that it's also not a function, and you would just call them both relations, inverse relations. But if they do pass those function tests, then they are inverse functions. So before I go to the next slide, I just want to show you a few things. The first thing I want to show you is the notation. So whenever we write a function, we can write it as y, but in this case, we're going to write it as f of x. You probably remember that from Algebra 1. And like I showed you before, when we write the inverse of a function, we're just raising this f to a -1. So we're going to write that as f to the -1 x. And this we say this as f inverse of x. We don't say this as f to the power of -1 x. We say this as f inverse x. So this is the notation that you're going to have to know. In addition, I just wanted to, let me get the eraser out. In addition, I wanted to bring up some applications from trigonometry. So hopefully from geometry, you remember your trig functions, your basic 3, your sine, cosine, and tangent. So I'll just bring up sine. So we have sine, right? hopefully you guys remember learning about the inverse of sine. So sine to the power of -1. And hopefully you remember talking about cosecant, which is the reciprocal of sine. So what I want you to just keep in your mind is that the inverse is not the same as the reciprocal. Because when we're trying to find the inverse, I don't want you all to try and find the reciprocals of these functions. So the sine inverse, so inverse of sine is not the same thing as the cosecant, because the sine inverse is not equal to the reciprocal of sine, which is 1 over sine, because cosecant is equal to 1 over sine of x, for example. So just keep that in mind. The inverse is not equal to the reciprocal. I just wanted to bring a trig application that you'll learn more about in pre-calc into play. So here's some essential understanding I want to go over before we get into our first practice problem. The inverse of a function may or may not be a function. So for example, if we're given function f and we find the inverse by switching the domain and range, we're not guaranteed, just because f is a function, we're not guaranteed that f inverse is also going to be a function. And I'll show you an example of how this comes into play. So the diagram I am going to show you in a minute or so has a relation r, and relation r, we already know it's a function because each element of the domain does not correspond to multiple elements of the range. It's a binary relation. So no, it's not a binary relation. Sorry. There are multiple. I think there's 4 components in the range. You'll see 4 numbers. Sorry, 4 numbers in the domain. And then those 4 numbers in the domain, 2 of them will correspond to the same value in the range. 2 of them will correspond to the same value in the second value in the range. So you can have it in such that multiple inputs correspond to the same output, but you can't have multiple outputs corresponding to the same input. So in this scenario, we have multiple inputs corresponding to the same output. That's relation R, and it is allowed. It's a function. It passes the vertical line test. That's fine. However, when you switch it to find the inverse of R, or R inverse, you're going to end up having the range becoming the domain and the domain becoming the range. In that case, we only had 2 values in the range originally, so in the inverse, we're only going to have 2 values in the domain. And those 2 values in the domain are going to correspond to multiple outputs, which we cannot have. That doesn't pass the vertical line test. Therefore, it's not going to be a function. The range of the relation, the range of the relation, which is our function r, is the domain of the inverse. So whatever were our y coordinates in function r are going to become our domain, or our x coordinates in our inverse. On the flip side, whatever was our domain of function r is going to become the range of our inverse. And here's that example I was talking about. Here we have relation r, and relation r is a function, because if you look at the domain, we have 1.2, 1.4, 1.6, and 1.9. In our range, we only have 2 values, 1 and 2. In this case, 1.2 and 1.4 correspond to 1. So we would have the points 1.2, 1 and 1.4, 1. But that's allowed because that would actually make a horizontal line, which passes the vertical line test. So multiple inputs can correspond to the same output. So multiple x coordinates can correspond to the same y coordinate. Same thing with 1.6 and 1.9 corresponding to 2. So this passes as a function. However, when we find the inverse of r, our r to the -1 power, we're switching the domain and the range. So in this case, our range was 1 and 2 for function r, so we're going to make that our domain for r inverse. So 1 and 2 become our domain, and then our range becomes the original domain of function r. So our range would become 1.2, 1.4, 1.6, and 1.9. However, in this case, we have only 2 components of the domain, and these 2 components of the domain correspond to 2 components of the range. So one input, one x coordinate in this case, is corresponding to 2 y coordinates, which we cannot have, because if you graph this will actually make a vertical line, and that does not pass the vertical line test, because when we do our vertical line test, our vertical lines that we draw are going to hit this relation in more than one spot at a single point, at a single x value. So x values can only correspond to one. So one x value can only correspond to one y value, but one y value can correspond to multiple x values. In this case, that is totally flipped. So the inverse of r, or r inverse, does not qualify as a function. All right, so let's get into our first practice problem, problem number 1a. There's 2 parts to this problem. So in this case, we're going to find the inverse of a relation. what is the inverse of a relation S that we're going to be given? So here's relation S. It's given in the table. Our x coordinates are 0, 2, 3, 4, and their corresponding y coordinates are -1, 0, 2, and 3. You can see that this is a simple xy table. We're going to find what the inverse of relation S is, so what S inverse is. So here's your solution pre-written. You can take a look at that, but I'm going to be going through that with you again now. So first we're going to talk about what is the inverse of S. So inverse of S, we can write this, if you remember the notation I went over, inverse of S is equal to S to the -1. That's how we would write it. So we're pretty much going to be making a XY table that reflects the XY table that was written for relation S. So how are we going to find out what our coordinates are? Well, to find the coordinates, we're going to swap the original coordinates. So swap original coordinates that came from relation S. Because remember, the domain of the function is going to be the range of the inverse, and the range of the function is going to be the domain of the inverse. So all we need to do is we just need to swap our x and y coordinates to change the domain and range. In this case, if you remember that relation where we said if in the original function or relation A pairs with B, then in the inverse B is going to pair with A. So in this case, our x coordinates are going to be equal to A, and then our y coordinates are going to be equal to B. So in this function, in this relation S, we have the coordinate points A, B, but in the inverse, we're pretty much going to swap them, so we rewrite them as BA. So how are we going to do that? Well, let's take all of our x coordinates, 0, 2, 3, and 4, and we're going to write them under y this time. So we're going to write 0, 2, 3, 4 under y. As for our original y coordinates or our range, we're going to write them under x for our inverse. So -1, 0, 2, and 3, and this is our answer. So this is the inverse of S, which is S inverse. Let's move on to problem B. So in this problem, we're going to find the inverse of a relation again. We're going to pretty much be working with that same relation as we were talking about, but this time we're going to be representing what are the graphs of S and its inverse, S inverse. So here's your solution already pre-written. You can see that we have a graph and then we have two tables to find the answer to this problem. So I'll be going through that again with you. So let's just establish what are we putting on this graph. We're putting relation S on this graph. But before we even plot points on a graph, don't we need XY tables so we know what points we're plotting? And the answer to that is yes. So let's first find out what the XY coordinates of relation S are. So our XY coordinates, remember, are A, comma, B, and we've already given that on the previous slide. So I'm pretty much just going to rewrite what we were given on the previous slide. So we had 0, -1, 2, 0, 3, 2, and 4, 3. And we already found S in the inverse of S, which is S inverse. We already found the XY table on the last slide, so I'm going to copy what we had on the last slide onto this slide. And S inverse, and if you forgot or anything like that, you simply know we're swapping the X and Y coordinates. So whatever's in our column for our X values here, we're going to write it in our column for Y values. So 0, 2, 3, and 4. And whatever was in our Y column, our column of y coordinates for relation S, we'll write it in the column for y coordinates for the inverse of X, inverse of S. So we're going to write -1, 0, 2, and 3 down. So these are our XY columns. And again, if you didn't know, all you had to do is take these coordinates here and you had to swap the coordinates. To find what the coordinates for S inverse was going to be. So S inverse. All right, so now let's graph these points. Let's first start with the relation S. So we have the point 0, -1. So we start at the origin and come down 1 point and then draw a circle there. Then we have the point 2, 0. So we're over here. We come right to, but we don't have to move up or down the y-axis at all. So we're going to plot our point here as well. Our next point is 3, 2. So come to the right 3 and up 2. And then our last point is 4, 3. So come to the right 4 and then go up 3. That is relation S. Now we got to graph in S inverse. So S inverse, the first point is -1, 0. So we're going to the left, -1, but we're not moving off the x-axis. Then we have 0, 2. So we're starting at the origin and going up 2 points. Then we have 2, 3. So going right 2 and then going up 3. And then our last point is 3, 4. So going right 3 and going up 4. As you can see, hopefully you noticed, there's actually an axis of symmetry right here. So I'm drawing a dotted line, and this represents our axis of symmetry. And our axis of symmetry is actually going to be y equals x. So this is going to be our axis of symmetry. So you're probably wondering, what is the axis of symmetry? So symmetry is when you split a shape or a figure down the middle, and then you're able to split that shape so it has two reflected or identical sides. So in this case, if you see relation S is pretty much reflected across y equals x to find the inverse of S. So y equals x is going to be our axis of symmetry. It goes right down the origin. As x increases by 1, y is also going to increase by 1. Or if x decreases by decreases by 1, y is going to decrease by 1. It's a linear relationship. If you actually graph that, you'll see that the relation S is reflected across this axis of symmetry to give you the points for S inverse. And this applies to pretty much any inverse. So just take that into, just make sure you notice that. So our next problem number 2a, we're going to find the equation for an inverse after we've been given the equation for the relation or function we're going to be working with. So in this case, we're going to find the inverse of the function y equals x squared minus 1. We already know this is a function because it's a quadratic binomial in this case, so it's pretty much our parent function x squared, but it's moved down to, instead of having the vertex as the origin, we moved it down to -1. So that is the function we're going to be working with, and we're going to be finding its inverse. So here's your solution already pre-written. I'm going to go through this again with you. So whenever we are given the equation for a function or a relation, we're trying to find the inverse, the first thing we are going to do is we are going to take the function or relation we've been given, and we are going to switch x and y. And I'll show you what that means in a second, but I think that's pretty straightforward. And then our second step is pretty much going to be solving for our y. And that's really it. There are only 2 steps. These problems are really not too complicated. So when we have, I'm going to rewrite the function we've been given, y equals x squared minus 1. Our first step is to swap x and y. So whatever was y in the original function, I'm going to rewrite it as x, and whatever was x in the original function or relation, I'm going to rewrite it as y. So x equals y squared minus 1. You're pretty much just literally switching the variables. Afterwards, we're going to solve for y now. So we're trying to get y by itself and have our new inverse be y equals whatever is on the other side of the equation. So our first step is to add 1 to both sides. So we get x plus 1 is equal to y squared. And our second step, well, that's pretty much all we have to do. All we have to do is square root both sides to get y by itself, because the opposite operation of squared is square root. So we're just going to square root both sides, and we're going to get the positive or negative square root of x plus 1. Make sure you write a positive or negative, because there are oftentimes students will write just the square root of x plus 1. You're only taking into consideration the principal root. You're not taking into consideration the negative root as well. And because we're working with inverses, and because this was originally a function, you have to take into consideration the principal and the negative square roots. You can also write this as f to the -1, or f inverse. That's how we should say it. Is equal to positive or negative x plus 1. And that's your final answer. All right, let's do one more problem. Same thing. This is going to be just problem number 2b. We're going to find an equation for an inverse after being given the equation of the function or relation. So the function we've been given is y equals 2x plus 8, and we're trying to find the inverse of this function. We're going to use the same 2 steps from the previous problem in this problem to find the inverse. So here's your solution already pre-written. I'm going to go through it again with you. So again, the first step was switching out the x and y. So switch x and y. We're swapping the variables, pretty simple. And then afterwards, you're going to use basic algebra to solve for y to find the inverse. So I'm going to rewrite the function we've been given, y equals 2x plus 8. And we're going to swap the variables. So we're going to write this as x equals 2y plus 8. To get y by itself, I'm going to subtract x from both sides. So x minus 8 equals 2y. And then to get y by itself, I'm going to divide both sides by 2. So 2y divided by 2 is just y. X minus 8 divided by 2 is just x minus 8 over 2. And if we want to simplify this further, we can write it as y equals 1/2 x, because remember there's an imaginary 1 coefficient in front of x, so 1/2 x minus, 8 divided by 2 is just -4. And we can write this as f inverse of x is equal to 1/2 x minus 4. And that, folks, is our final answer. So pretty straightforward. All right, that's all I have for you today. Hope you enjoyed the video, and please check out the other functions and inverses videos that I make coming soon. If you like the video, please hit the like button, the subscribe button, the post notification bell, and comment and share. You can always check out our website, and you can email us at our Gmail with any questions or concerns. We're always open for communication. Again, I hope you enjoyed the video, and please stay tuned for more. Thank you. See you next time.